Hello. Hi. So last time, of course, and the time before, we looked at the definition of vector space and we tried to get some sense of examples of vector space. So there are many different kinds of vector spaces: 2 tall vectors, 3 tall vectors, 2x2 matrices, 3x3 matrices, 2x4 matrices, quadratic polynomials. There's a whole lot of vector spaces, and we tried to see a number of examples and to check through the conditions in the definition to verify that they are all vector spaces. I a number of times mentioned that condition 1 and condition 6, the closure conditions, are the ones that we'll worry about most of the time. They prove to be the ones that are the trickiest, the ones that are kind of the key, the sort of central point of the matter. So with the check-in today, I want to reinforce a little bit what makes something a vector space and also give a little bit of a suggestion of what's coming. So here we go. It says this is a plane through the origin in R3, and I want to verify that it's informally verify that it is a vector space by showing that if you take two members and take kind of an arbitrary linear combination, you get a member. So I'm just going to do kind of a made-up couple of examples, and then down here it's the same thing with another kind of space. So first example, I look at the set of x, y, z's where x plus 2y plus 3z is equal to 0, and I'll just make up two vectors where x plus 2y plus 3z equals 0. I don't know. V1, x plus 2y plus 3z equals 0. So how about 3, 1, so that's x plus 2y makes a total of 5, plus 3z equals 0, so minus, 5/3. All right, x plus 2y plus 3z is equal to 0. And then take another one, v2. So x plus 2y plus 3z equals 0. So how about if I say minus 1 and 1 and 1? Okay, and both of them have the property that x plus 2y plus 3z equals 0 and x plus 2y plus 3z equals 0. I'm going to take just an arbitrary linear combination. I don't know. How about if we take 6v1 plus 4v2? And I'm going to check at the end, when I get to the end, I'm going to check that x plus 2y plus 3z equals 0. So let's see if I can do this. This is always the hard part. So that's 18, 6, and minus 5/3 times 6 makes minus 10. 4 times v2 is 4, 4, and minus 4. And I add them together, and I get here 22, 10, and minus 14. So is it the case that 22 plus 2 times 10 plus 3 times 14 equals 0? So let's see, 22 plus 2 times makes 42. 3 times minus 14 is 3 times minus 10 is minus 30. 3 times 4 is, so it is indeed minus 42. Okay, so that of course isn't a proof. You'd have to do a proof with x's and y's and z's, but nonetheless it's some kind of reminder that the point of a vector space is that you can take linear combinations, and when you take a linear combination of things from the space, you get a thing from the space. That is to say, vector spaces are closed under linear combinations. This is an illustration that vector spaces are closed under linear combinations of two of their members. Of course, you could take 3 members or 4 members or 5 members. I just happen to pick 2 just to do an example. Okay, I remind you back to the screen. Oops, went the wrong way. There we go. Remind you back what the second question is. It's the set of x, y, z's where x plus 2y equals 0 and z equals 0. That's a line through the origin because you have one free variable, y. And I'm going to pick two 3 tall vectors that have that property and do a linear combination of them. So let's get rid of it and see how we do with 2. So v3 and v4. So let's see, x plus 2y equals 0 and z equals 0. So the z equals 0 part is not hard. X plus 2y equals 0. How about if I say 2 minus 1 And how about if I say 3, and then I need to have a negative, so negative 3/2. All right, I think it's the case that x plus 2y makes 0 and z is equal to 0, and x plus 2y makes 0 and z is equal to 0. So I think I'm good. Now I'll take a combination of those folks. Oh, how about 1 times v3 and minus 5 times v4. And at the end, I'm going to check that x plus 2y makes 0, and furthermore, z is equal to 0. So what the heck do I get here? So I get 2 minus 1, 0. And then I got to do 5 times v4. So I got 15. 5 times minus 3/2 is minus 15/2, and 0. I don't know. So that's 17. So that's 2/2 minus, so that's minus 17/2, and 0. And indeed, a person can see that x plus 2y does indeed make 0, and z is equal to 0. So I do have closed in this particular case. I do have closed in this particular case. You'll notice also that the question asks not just to check that it's a member of the line, but also to check that it's a member of the plane, meaning this plane up here. So let's try that. Is it the case that in all three of these, that if you take x plus 2y plus 3z, you get 0? Well, that's right. X plus 2y plus 3z does give you 0. In all three cases, the z equals 0 part means the question boils down to x plus 2y equals 0. So the point of that question was just to notice that really this line is a subset of this plane. This line is the specialization z equals 0 of this plane. So this line is a subset of this plane, and for that matter, this plane is a subset of 3 space. So all these vector spaces are kind of nested inside each other, so you can have vector spaces that are somehow subsets of other vector spaces. And that's what we want to talk about today. Vector spaces that are subspaces of other vector spaces. So for any vector space, a subspace is a subset that's itself a vector space under the inherited operation. Inherited operation just means that in all three cases that we were looking at in the check-in, R3, the plane through the origin, and the line that lies in the plane, the line through the origin, all three of those, you add two vectors in the same way, you add them component-wise, and you multiply vectors times a scalar in the same way, you multiply component-wise. So they all share the same operations. Any vector space has a trivial subspace. We saw that last time. At the opposite extreme, any vector space has itself for a subspace, because it is indeed a subset of itself. A subspace that is not the entire space is called a proper subspace. Just a word, just a vocabulary word. And we've seen already, besides the check-in, we've already seen that the line y equals 2x, the second component is twice the first, is a vector space. And I'm just noticing that's a subspace of the plane. So the line y equals 2x here that we checked earlier is not just a vector space in its own right, but it's also shares the operations with the superspace, shares the operations with the plane, shares the operations with R2. So S is a subset of R2, and that makes it a subspace because it's the same operations. Okay, so a subspace gives me more examples of vector spaces that I can talk about, and also introduces a new idea at the same time, so it's economical. The collection of 2x2 matrices we know is a vector space. You can take combinations of 2x2 matrices and you get a 2x2 matrix. You can also you can also look at the collection of 2x2 matrices that have some limitation on them. This is a collection of 2x2 matrices with the property that the upper left and lower left are the same number, and the upper right and lower right are the same number. If you like, you can rewrite it this way, and we will like. If you like, you can rewrite it this way, that this is A times 1, 0, 1, 0, plus B times 0, 1, 0, 1. And you recognize this as what we called in the first chapter parameterization. We brought the A and the B out as parameters, so that I'm expressing vectors of this form as a sum, a linear combination, of two vectors here. And this is a vector space. clearly a subset of the 2x2 matrices, so it's going to be a subspace of the 2x2 matrices, and what we're finding is that vector spaces can have inside them vector spaces, and this is just an example. So again, one of the best ways to understand what something is to give examples of it not, to contrast the examples of it yes with the examples of it not. You understand what a dog is in part by pointing to things that are not dog. That's a cat, that's not a dog. So this is an example of something that is not a subspace of R3. It looks like a plane through the origin, except that it says 1 instead of 0. So because it says 1 there, it's not a plane through the origin. So it's perfectly well a subset, but it's not a vector space. For example, it's not closed under vector addition. Here's two members of capital T, and when you add them, you get something. It's a perfectly legal thing, but it's not a member of capital T. X plus Y plus Z doesn't add to 1. It adds to 2. So although it's a perfectly good subset of R3, it isn't a vector space, and so that makes it not a subspace. So one of the things that a person kind of gets their antenna up, pays a little attention to, is the fact that that's a 1 and not a 0. There's a little something about zeros that happens here. And the key result in this section is this one here. It says if you have a subset of a vector space, then each of these three statements say the same thing. They say something that we've noticed many times in the few videos that we've been doing so far, but we've noticed that it's about linear combinations. So a subset of a vector space is itself a vector space, provided that it's closed under linear combinations of pairs of vectors. We've often taken linear combinations of pairs of vectors. And also, that's the same thing as saying you can take linear combinations of any number of vectors, R1, S1 through Rn, Sn. All three of these statements say the same thing. They're equivalent statements. So 1 is the same thing as 2, 1 if and only if 2. 1 is the same thing as 3, 1 if and only if 3. 2 is the same thing as 3, 2 if and only if 3. We will often find 2 to be the most convenient, not the only one we'll ever use, but we'll often find it to be the most convenient way to state what's happening. And you notice that this lemma really captures what I've been trying to emphasize now for some time, that vector spaces are about linear combinations of the members. In particular, vector spaces are about closure under linear combinations. Closure of 2 or closure of n, it's not important, but about closure. Vector spaces are about, you can take a combination, linear combination, of the members of the space, and you're sure to end up in the space. You're sure to end up in the space. Okay, and as so often happens in here, the videos are an introduction to the material, so the book has the complete proof, but I'm going to try to go through the basic idea here, so that you remember that in the first example of vector space, the line y equals 2x, I commented when we were checking several of the conditions that they don't depend on the y equals 2x part, they just depend on sort of the addition. So for instance, x1 y1 plus x2 y2 equals x2 y2 plus x1 y1 the proof of that didn't use the fact that the second component is twice the first. It just didn't need it. So it turns out that to show something is a vector space, and to show something is a subspace, we will only need to check closure under linear combinations. You can check closure under linear combinations of 2, if that's most convenient in the space you're looking at. You can check closure under linear combinations of more than 2, if that proves to be convenient. But once you know you're inside a vector space, the important thing is, the kind of key idea is linear combinations land you back in the space you're in. Linear combinations land you back in S. And I'm going to do a number of examples, and oh, I'm sorry, I forgot I was supposed to go backwards. There we go. I'm going to do a number of examples, and as we move through the examples, I'm going to be emphasizing something that appears, something that's emergent, and that is that this idea of parameterization here proves to be a key one. This idea of bringing out the A's and B's, or C's and D's, or whatever letter they are, proves to be a key one. Okay. So here we'll start here with the vector space of quadratic polynomials, and we've already checked that that's a vector space, or at least we pretended to check that that's a vector space. The basic idea there is that a linear combination of quadratic polynomials is a quadratic polynomial. Of course, there are 10 conditions to check, but nonetheless, it has a conceptual basis. If you look at the quadratic polynomials that have the property that a2 equals 0, then you're looking at linear polynomials. I'm claiming that linear polynomials form a subspace, it's capital L, forms a subspace of the quadratic polynomials. To verify that by the previous lemma makes verifying that very easy. You don't need to check all 10 rules. You only need to check closure under linear combinations. So I did. I wrote down r times the first plus s times the second. So I have r times a first linear combination and a linear polynomial plus s times a second linear polynomial. And when you distribute the r's and add together, you get a constant term, a coefficient of x. This is a linear polynomial. It's got a constant term. It's got some letters there, but it's not hard. It's a constant term. That's a real number. And a coefficient of x. And again, that's a real number. It's a somewhat convoluted way to write a real number, but it's a real number. So real number plus real number times x, that's a linear polynomial. So the right side is a linear polynomial with real coefficients. So capital L is closed under linear combinations, and by the prior lemma, linear combinations of 2, by the prior lemma, that's enough to show that it's a subspace. You don't have to check that scalar multiplication distributes over addition. You don't need to check any of those things. You just need to check closure under linear combinations. Another example of a subspace, so I'm looking at a subspace again of quadratic polynomials. Another example of a subspace is when the quadratic polynomials have all 3 letters the same. Do you see it says A? So for example, 5 plus 5x plus 5x squared. 8 plus 8x plus 8x squared. Minus 2 plus minus 2x plus minus 2x squared. And here you see I brought out the A. So this parameterization where you bring out the A is something we're going to find very convenient as we move through. It's just a small little gadget, but it proves to be a convenient gadget. To check that this collection is a subspace, all I got to do is check that it's closed under linear combinations of 2. So I'm only going to do 2. I'm not going to do 3 because I don't need 3. I can get away with 2. So r times one of them plus s times one of them. Of course, it doesn't have to be AAA. In both cases, it might be AAA and BBB. And when you do the algebra, it's not hard to do the algebra. You get RASB for the constant term, RASB for the coefficient of x, RA plus SB for the coefficient of x squared. That's 3 equal coefficients here, 3 equal numbers. And that's exactly the criteria to be a member of A, is to have the same constant term coefficient of x and coefficient of x squared. So that means that it's closed under linear combinations. So that means that by the prior lemma, that means that it's a subspace. And again, the parameterization here, the fact that I brought the A out and just expressed this as all multiples of 1 plus x squared, capital M is all multiples, all scalar multiples, of 1 plus x squared, any scalar you like, to 108 minus 4.3. That parameterization proves to be a very convenient way to understand vector spaces, and we'll talk about that more as we move through, but just giving you a little preview. Okay, and here's another example of this subspace is a plane. It's a plane through the origin. I want to illustrate that you can also understand it as parameterized, and then that makes it easy to show that it's closed under linear combinations. So to parameterize the plane, I think of 2x minus y plus z equals 0 as a linear system that has only one equation. When you think of 2x minus y plus z equals 0 as a linear system with only one equation, then the leading variables x, y, and z are free. So you express x in terms of y and z. There it is. Express x in terms of y and z. Y and z are free. And so you're looking at this description of capital P. These describe the same set. This is a collection of vectors. This is a collection of vectors. They contain the same vectors. Now to parameterize, it's got y's and z's, so I got to bring out the y's and z's. So here they are over here. These are the things associated with y, the numbers associated with y. These are the numbers associated with z. So I took this description and parameterized it to get this description. I'm trying to get across why I'm interested in the parameterization as part of showing that something is a subspace, why parameterization is so darn convenient, and so I'm just about to get to that. This is copied from the previous slide, didn't all fit on one slide. I want to show that a linear combination of two of these makes a third that is one of these. So here I go. Here's one of them, y1 plus z1. Here's another of them, y2 plus z2. I took a linear combination, r1 times the first, r2 times the second. I want to show that the result is the third of these, that it's something times this vector plus something times this vector, and of course it is. r1 y1, r2 y2 added together times the first, r1 z1, r2 z2 times the second. So when you have the description parameterized, it's very easy to see that a linear combination of two of them makes a third that's of that form. So the fact is that capital P, as opposed to what's on the previous slide, this description here doesn't make this so plain. Capital P describes, this description right here describes members of capital P as a linear combination. Right? Isn't that what it does? Not so much on this slide. Doesn't show you how members of capital P are a linear combination. But down here, members of capital P are explicitly written as a linear combination. And down on this line here, we are taking linear combinations of linear combinations, and the result is a linear combination, which we knew it had to be because of the linear combination lemma. That's that little, it's a very small observation, but it proves to be at the heart of everything we're doing. A linear combination, R1 and R2, of linear combinations, y1 times the first plus z1 times the first, y2 times the second, z2 times the second. A linear combination of linear combinations is a linear combination. Okay. So the parameterization brings out the linearity and will prove to be a key to understanding what's happening as we move through doing more and more of these. We're going to keep wanting to say, how can you describe this vector space or this subspace in some way? How can you describe it as a linear combination of things? How can you parameterize it? And that will make many of the problems give you an answer. Another example of the same thing. I don't like to do one example. I especially don't like to do one example when it's a very key idea. Okay, so these are 2x2 matrices, and they have the property that A equals B, also that C equals B. Again, these are 2x2 matrices that have the property that A equals B, and also that C equals B. So basically, the upper triangle here are all three the same number. The bottom part of the triangle, the D, could be anything it likes to be. So you might have, for example, 3, 3, 3, 5, or 1, 1, 1, 0. That's a perfectly good collection of 2x2 matrices. I'm claiming that it's a subspace. In order to show that it's a subspace, I'm going to do what I'm illustrating. I'm going to parameterize it. Let's go. C, 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 D. I took the upper left, C, 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 and D can be anything it likes. I parameterized. I broke out a C part and a D part. And now I've explicitly written members of capital Q as a linear combination. So when I go to take R1 times the first plus R2 times the second, I'm looking at a linear combination of linear combinations. So this is guaranteed to be a linear combination, and you're starting to see some first hint that linear algebra has the property that this is just a hint, but that it all kind of fits together. It's that linear combinations are the tie. It all makes sense. A person can say it's the same thing over and over again, or you can say it all makes sense. There are themes, and I'm going for the second. Okay, so we've expressed this set as a linear combination then we showed that we showed closure under linear combinations because this boils down to a linear combination of linear combinations, and so we were done. Okay, next time we'll introduce the general word for what it means to say that something is the collection of all linear combinations, and we'll work some more with the ideas there. Okay, so let's see here. I got to bring my next time window up. There we go. So next time we're going to do subspaces again, and we're going to again bring out the themes of linear combinations, that it's about figuring out in what way these things are unfettered, free linear combinations. Okay, very good. Bye-bye.